Okay. Oh yeah. Okay, now it's on. Okay. So what we're gonna do, guys, all right, is we're going to go through this problem. Now, I want someone to tell me what is going on in this problem. Someone give me a high level, 30,000 foot view, Brylan. What's happening in this problem?
So there's a man.
Mm-hmm.
He is pulling with a set of pulleys a rock.
Yeah.
That is 100 kilograms.
Yeah.
And we are trying to calculate all the forces and the weights and all of that good stuff in which direction they go.
Okay, what's happening with the rock?
The rock is not moving. Of course, gravity is not moving yet. Because the gravity is like holding it how many?
The gravity's holding it.
Newtons.
Sure. Okay, good. And then what's keeping it up?
The little man with the pulley.
Well, how is
his force is X force to the left. The tension of the rope.
Right. He's creating tension on the rope, which is pulling what? Up on the pulleys, right? On the two pulleys. What about the pulley at the very top right? This pulley up here, what's it doing? What's it do? What's the rope doing to this pulley here, guys? It's pulling it down, right? This rope is pulling these up. This one's pulling it down, right? Over here, what's happening? The rope is doing what to this pulley?
Pulling it down.
It's pulling it up and to the left. Tucker. Okay? It's going up and to the left. Up and to the left. Up and to the left. Up. It's not moving, but it's being pulled up and pulled to the left. This one right here. It is. It's not turning at all. There's a force pulling up on it. Just because it's not moving doesn't mean there's not a force pulling on it. This is the whole point. Okay. All right, we're in a tug of war. The force on the pulley. The force on the pulley. It's not the. I'm sorry? It's not going up, it's being pulled up. It's being pulled.
So it's resisting.
No? Okay. This is important. Okay, if it's a tug of war, you have the end of the rope, I've got the end of the rope. I'm pulling and you're doing what? You're pulling.
Yes.
If we're at a standstill, we're not moving, right? Nothing's moving. But you're obviously pulling, right? You're pulling that way. What happens if I start to come down and I pull over that direction, pull to the left? Then which direction do you have to pull? That way, right? The pulley is being pulled up because of the rope. It's being pulled to the left because of the rope. But right now, because of the bracket, it's standing still. It's not moving. If the bracket breaks, it's going to fly. But it's being pulled both up and to the left. Let's do this. This is important, guys. All right, let's do the.
Confused on the difference between like the force on the pulley.
Yeah, let me do the. Let's do the free body diagram. Right, the first thing we have to do is.
I don't even know like what direction you mean by up or by left.
Well, what direction's up?
Well, okay, but how's it
Because it's got a rope. The rope is being pulled up, and the rope is being pulled to the left. Who's pulling it to the left? Who's pulling the rope? Shh. The force on the pulley. Shh. Who's pulling to the left? The man. What's pulling up? What's pulling up? This rope here, right? Because
But isn't that going down because the man's pulling left, so wouldn't it like...
it's not moving. Nothing's moving.
The rope isn't moving?
No, we talked about that. Standing still. The idea is that we're standing still. We're at our net force equals 0. We're standing still. So the weight is hovering because the weight is pulling down on the rope here, which is really because of this pulley, it's pulling up on this rope here. You see what I'm saying? The down here really is a pulling up of this, right? Which is really pulling that up. Does that make sense? Okay, I just want to make sure we're clear. All right, does that make sense, Avery? Okay. All right. So, but I think the issue of up and down, right, is an important one because tension. Hey guys, seriously, if you need to do that, you can do that in Mr. Gunnan's office. I hear a bunch of giggling, and I'm done with it. The issue with the ropes, Addison, is that you're right. Because the rope, if Avery and I are pulling the rope, she's pulling one direction, I'm pulling the other direction. But the force in the rope is whichever we're pulling, right? If she's pulling 10 newtons one way, I'm pulling 10 newtons the other way. The tension in the rope is 10 newtons. But she's pulling opposite than I am, right? It's all relative. So your question about what direction is up is really valid. But you got to think about, it really depends on what pulley you're talking about, right? Because the rope is pulling up on this pulley, but down on that pulley. And that's kind of messed you up, didn't it? Yeah. But that's why I want to give you guys a process for the free body diagrams. Okay? When we do the free body diagrams, what's the first thing we do before we draw the free body diagrams?
You circle what you're going to do.
Okay. Yeah, we're gonna make those boundary boxes, right? Okay. So what would be the things that we want to make the boundary boxes around? Antonio, give me one item.
It can be pulley.
There's like 4 pulleys.
The 2 pulleys for the rock. The 2 pulleys for the rock. Sorry, guys.
I know it's been a long weekend. I get it. All right. Okay, so there's the 2 pulleys, right? Now, do I include the rock or do I not?
No, you don't have to.
I can, but I don't have to. There's nothing else coming off the rock. And the force, if I'm doing this, it's really the force in the bracket. But we know the force in the bracket really is the force of the rock. Does everyone get that jump? Everyone get that jump? Okay, because I want to make sure. You were there, Jack? You got it? Paul, I keep doing it again. Sean, you good? Okay. I'm going to call him Paul. I had a buddy of mine named Paul Bertalin, and I worked with him, and everyone at work would call, half people would call him Paul, the other half would call him Bert. I was like, is his name Paul or Bert? And that was like short for Bertalin, and I was like, it took me like, I didn't know. Anyway. All right, so what's the next thing we're going to write a box? Yes.
The pulley at the very top.
The pulley at the very top. Okay. What's the next item, guys?
The pulley, the other one. But not including his hands.
Tucker?
Tucker's shaking.
Heimlich? Is it the Heimlich maneuver?
I'm calling on something.
All right. Austin, what's the other one? What's the other?
One of the other pulley at the very bottom.
Okay, other pulley at the very bottom. Shh. Now, okay. I'm going to do one more, which is this guy about the hands, okay? Just for the heck of it. All right? Okay. Now, what are my forces? Let's talk about the forces. In this box, in each of the boxes, you ignore what's inside the box. What is coming out of the box?
Tension.
Where?
On the top.
On the top. There's one tension. What else is there? Is there another tension?
Yeah.
Okay, there's another tension here.
There's also an FG, which is the gravity.
Okay, there's an FG here, right? Okay. What else? Okay, is there anything else coming out of that box? No. Okay. So I'm gonna move this box.
That little doohickey's kind of cool.
Yeah, I love this thing. All right. So now, what about the next box? This box. What forces are here?
There is a tension.
What else is coming down over here? Tension.
There's also a normal force.
Not a normal force, but a force of the ceiling or some force up.
That's not normal.
No, normal is a reaction force. There's a normal force on the ceiling.
So you're telling me it's not reacting to them?
It is a force of the bracket holding up. The bracket is having to hold up.
Okay.
Technically, you're right.
Is
It's a-
FBY?
Huh?
FBY.
Sure, you can call it F pink elephant. It really doesn't matter. But then that's fine. The FBY is perfect. But you're right. It technically is a normal force within the bracket. And I'm trying to save the normal forces for the flat spaces. Okay, to keep it clear. But you're right. Huh? So I just put FC for ceiling. You can put whatever you want. Okay. Or actually, no, you're right. Actually, I asked for FB1, didn't I? So we're going to call it FB1. Sorry. I got it. So I'm going to move that over to here. Right there. Okay? Then, and again, we ignore what's inside the box. Right? What about this guy right here? What are my forces on this one? This is the big one, right?
You've got the tension.
Tension where?
On the top part.
What else is there?
You got an FM.
I'm going to erase this dude for like 1 second, okay? We have a tension where?
You got an FM.
Well, right now we have a tension in the rope. okay? And it will, but the reason I'm going to keep it as tension, okay? Ultimately, that tension will equal him, his force of the man, right? But we're going to leave it as tension for the moment, okay?
And then you have an FBX.
Okay, let me do this for a second. I'm going to move this guy out of the way for a second. I'm going to move to the side. Let's look at this. Now, I have two forces on here. This is very important, guys. Very important. I have two forces, which are tensions, right? Right now, as it's drawn, what is this free body diagram telling me about the box?
That there has to be two other ones.
Okay, but as it's drawn right now, it's moving, right? Because I have unbalanced forces, you're right. But in order for it to stand still, then I have to have
A normal and an FBX.
I have to have a responding Y and a responding X. Okay, this is why, when Tucker said this before, when we had this conversation, it's being pulled up and to the left. Do you see that? That's what's being pulled. It's being pulled up from the tension and to the left from the tension, right? But in order for it not to move, we've got to have an opposing force, FB2X. And by the way, looking at this here, what is the item, the physical object? What's the physical object creating this FB2X? The bracket, right? The bracket's holding that pulley from shooting off to the left. What's holding the pulley from shooting upward? What physical object holding that that pulley? The bracket is also holding it vertically, right? It's kind of trying to be bent, pulled and bent. So there's another force, FB2Y. Do you guys see that? Everyone with me? Okay, cool. So there's these two other forces here, right? There's keeping that puppy from moving. All right?
Wait, so
It keeps that kitten from moving.
even there's not anything technically like going down, because there's not anything coming out.
But the bracket is. The bracket, right, because the bracket is being...
Okay, so it doesn't work like you
Yeah, but what ends up happening, and we haven't gotten into this, is actually creating a bending moment. It's trying to bend it around this point right here. We'll deal with torques in a minute, don't worry about it. It's trying to bend it around this point right here. It's trying to bend it up, right? But that's a whole moment issue. We'll deal with that later. Okay, so the last one is the box around his hand, right? What forces are coming out of... What forces are coming out of his hand here? What are the forces coming out of here? We got what? Tension to the right and the force of the man. Now, I'm sorry, I don't mean to be man-centric here, but this is the scenario. Okay, so we got boom, 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 boom. All right, does that make sense? Okay, now that I have the free body diagrams, here's the best part. I don't need this anymore. I'm done with that. Okay, all I need is this.
Wait, which was it, man?
I'm sorry? What was you got it or no?
Yeah, that one.
Okay. All right, I'm going to bring this stuff up here. By the way, I was just talking to Miss Mulroy. She might actually buy one of these things for our class.
Oh, man. All right. What?
She might buy one of these things for art class.
You
For
want
our
to see the
class.
guy,
The guy that got me, yes.
man? Wait, what was
Oh, it's so funny. Yeah, that's what I hear. All right. Okay, I'm gonna miss you guys. Okay, here we go. All right. So, what's the point? What's the point of doing this? What's the point of doing this? Simplifies it and what? I can't hear you. But but how is it defining the equation? It's doing what for us? What's it doing with our forces? Well, it's accounting for all of our forces, right? We've accounted for all of our forces, and now from that, Abby, we can do what? Write an equation, not just find. It's like digging in the dirt, like, oh, there's one. Hey, there's another one. We're writing an equation. We have the power to create our own equation. There's another one. Quick, get it. Okay, I'm just a little giddy. All right, so I think so. So in the first free body diagram, in number 1 here, how many directions, this is kind of a misleading question, I apologize, but how many directions of force do we have? 2, X and Y. Some people are like, well, we have 3. I get that. I know we had 2 up and 1 down. We have 2 directions. We have, no, wait, I'm sorry, take that back. No, I'm, back, I was wrong. We have 1 direction of force. Yeah, that was why it was misleading. So we have, I know we have up, we have down. We have 1 direction, we have the Y direction, right? We have 2 directions in the Y. Okay, all right. The reason I asked that question is to determine how many equations we're going to write, right? It was misleading, I admit that. Okay, yes, so some of the forces in the Y. What are my forces that I am summing? What does the word sum mean? Okay, what forces am I adding up? Force of gravity plus tension plus tension. Okay, what does that equal?
0.
Wait. What? Okay, let me ask, what kind of thing does it equal? What were you saying, Tucker?
Reaction force. I was just saying the force. Reaction weight.
I can't hear over Rylan. Shh.
I think what I was going to say was wrong. I was going to say the force in the y direction.
But what kind of force? It's a net force in the y direction. You are correct. You're 100% correct. Bing, bing, bing. We are summing forces. This item here, FG, is what kind of a thing? What kind of thing is F of G? It's a weight or a force. It's a force. What kind of thing is tension?
A force.
A force. Tension is a force. What kind of thing is the other tension? A force. Good. Glad you got that. All right, if I'm going to add 3 different forces together, what kind of thing am I going to get?
Oh my God, another force.
Another force, a net force.
Wow.
And what does, this is important, no, I know you guys think this is silly, but this is important because it's important to understand this because it's not always going to equal 0. That's what problem 2 was about.
I know, but I don't understand.
We're going I know, so that's why I want you to focus on this. Okay. So the net, what is force equal to? What is any force generally equal to?
Mass times acceleration.
Mass times acceleration. The rock has a mass. Okay, the rock has a mass. The pulley brackets all have mass. It has if it has a mass and it's not moving, how much acceleration does it have? 0. Therefore, my total net force is equal to 0 newtons. Does that make sense? However, if my thing is in motion and it has an acceleration, my net force is not going to be equal to 0. Okay. All right. In number 2, free body diagram 2, how many directions of force do I have? 1. What direction is that force? Y. What are my forces that I'm adding up? So FB1, T, and T. Does everyone see that? Okay. What does that equal?
2T plus T.
What? Net force. Beautiful, your net force. Okay. And what does the net force, if my object is not moving, what does my net force equal? 0 newtons. Okay. Okay. In number 3, how many directions of force do I have? 2. Sum of the force.
I thought we were doing 2.
I said 3.
I know except for my brain saw 2.
Sum of the forces in the x direction. What are the forces that I'm summing in the x direction, guys? Okay, that's going to equal what? Net force. X direction, FB2X.
Wait, X direction?
X direction, I'm just doing that first. You can do either one. And that net, if my object isn't moving, then the net force is 0. Some of the forces in the Y. What are my Y forces? What are my Y forces? And that's going to equal my net force, which is equal to 0 newtons. Okay? Last one, number 4. What are my forces in number 4? Well, how many directions of force do I have?
See, I find
One.
this irrelevant. I find this irrelevant.
What? My question of how many directions?
No, the force.
It is to a certain extent. The problem is, here's the thing. If you put in to here, FM, okay? Then FM, you have 2 unknowns. You have FB2X and FM, and then you can't solve it. You follow me? You see where I'm going there?
What I did was I pressed in FM. I did that tension going to the left is FM. Isn't that practically?
It is. You're making the leap, which is fine.
Couldn't be FM
But I
plus
want-
FBX.
Yes, but what I want to make sure though is that everyone doesn't. If we put in FM right here, the problem is you're left with an equation with 2 unknowns, and you can't solve for it. You're right, but the next problem will be more clear. Okay, and the jump is easier to make in the next problem. But in this one, and you don't have to do it. I get it. If you explain to me what you're doing in your work, that's fine. Okay, so some of the forces in the X, and those forces are T and F of M, assuming that we're not moving, our forces are equal to 0. Correct? Okay, what is the one actual piece of information that you know in this problem? Wait, what do you mean the weight? I don't know the weight.
100 kilograms.
I know the mass.
No, that's what you can figure out.
Okay, you can figure it out. So the mass of the rock is equal to what? So the weight
Times -10.
is equal to the force of gravity, which is equal to mass times acceleration due to gravity, which is 100 kilograms, times what, Brylan? Negative 10 what?
Meters per second quarter.
Okay. What the heck just happened?
Well, don't do that.
Oh, that was weird. Okay. Yeah. All right. So my force of gravity is equal to what? What's my force of gravity? Jack. Jack, what's my force of gravity? What units? Beautiful. Okay. Now, where do I plug in that F of G? To what? Okay, into my equation for number 1, right? I've got F of G, right? So negative 1,000 newtons plus 2t equals 0 newtons, right? So T equals 500 newtons, positive. Now, does that make sense? Is my T pointing up? Yes, that makes sense. So we're good. Okay, now that I have T, stop with the noise. Now that I have T, what can I do? Okay, let's go to the next one. In this case, in free body diagram 2, what direction is my T in? Negative.
But it's still going to be positive because it's children, right?
No, it's negative and negative. Both of them are negative. So it's 2 times T, which is negative 500 newtons.
Oh, sorry, yeah.
Does that make sense? Yeah? Plus FB1 equals 0 newtons, right? So FB1 is equal to what? 1,000 newtons, right? Everyone see that? This is a really simple problem, okay? So now I have my tension, right? In this problem here, my sum of my forces and my X, this is now the next one, right? This is my, oops. Okay, that's this guy right here, right? So this guy, sum of the forces in the X, right? So sum of the forces in the X is FB2X plus T equals F net. What is direction is my FB2X? Positive or negative? Positive, right here to the right. What about my T? It's negative, right? So that means I have FB2X plus what? My tension is what? Negative 500 newtons, right? Equals 0 newtons. So FB2X equals what? 500 newtons. So is it right? Does that jive with our free body diagram?
Is the tension negative
In the third one, on the X, tension is negative. That's why I put a negative 500 right there.
Oh,
Is that you good? You with me? Okay. All right. So now in the y direction, is tension positive or negative? Positive, right? 500 newtons plus FB2Y equals 0. So FB2Y equals negative 500 newtons. Right? You guys see that? Does that make sense? Okay. And now again, last thing, tension is 500 newtons to the right. So that means F of M is equal to negative 500 newtons. Is everyone with me on this? It's a very simple problem.
Of course.
Right?
Of course.
Okay. Could I have asked you, could I have given you some of the other, could I have given you the tension and have you figured out F of G or FB2X? Sure.
Of course, because we have to have one unknown. That's one boy, that's right.
5-second rule. 5-second rule. All right. Okay. So let's move on to the next. To the next problem. This one here. This is a tricky one, right? Because this one, guys, this one, what's the difference with this one?
You got it.
Avery. What? And therefore, my net force is what? Not equal to 0. Now, at the end of the day, when you add the net force and everything else, there isn't, my rule still applies. Everything in physics adds up to 0, right? I mean, that's the rule. That's the way you survive, is that nothing is created, nothing is destroyed. Okay?
Water.
No, it's never just, what?
Ice.
Are you kidding?
Where
Where does it go?
How can you just have water? How can you always get running out of water?
We're running out of water because it's moved somewhere else. It's moved into the ocean, or it's moved into the atmosphere, or it's moved into other locations. It's being moved around the world. It's just in a different location. We're really dry. Some other places are really wet. Think about that. On these, we have these huge droughts in California and those areas, but then we have these huge, massive storms everywhere else. It all comes out in the end. In the end of the day, it's always there. As a global scenario, no, we can't. It's here. Now, are we running out of liquid water? Maybe. Because as the temperature of the Earth rises, more water is put into gaseous or vapor form, right? Or think about this, right? We have all of the ice in the poles that are melting, and now that's just going in. The problem is it's now getting diluted into salt water, into water we cannot drink directly. That's why desalination plants are going to be, if we can figure out a way of cheaply and easily desalinating. Okay, which I don't know why they don't use evaporative measures. It kills me.
You should do it.
You make so much.
You should do it. You don't want to do it.
And then you can split it with us.
Yeah, because those are ideas.
Okay.
It's like idiots. So you can give it
Okay. How about I give you information and knowledge and you can get an A in the test?
But then it doesn't work.
Make sure you edit that part out in the recording so it doesn't take forever.
Yeah.
Bleep, bleep. Okay. All right. So someone describe for me, Morgan, describe for me this problem. What's going on in this problem? I'm sorry? That's it? That's the only thing going on is a guy's pulling a rock. No. Give me some more. Guys, Morgan has the floor. Morgan, continue.
There's another guy pulling back on the rock.
Uh-huh.
And there's a little
Shh.
over there on the other side of the thing that I don't know.
What is this weight doing relative to the other rock? It's doing what? Pulling which direction? Up. It's pulling up on the rock, huh? It's pulling the rock up a little bit. It's like when we stood on the scale and we lifted you up slightly. What's it in the end of the day? What's it changing? Oh my God! If I wasn't going to give you a sugar high, it's changing the normal force. Exactly, right? Okay. Tucker? Do you want the candy? Or you want to bequeath it to somebody else? All right, Tucker. Give me a guy. Give me a person. Quick. Who wants it? You can't pick? All right, here we go. No.
This is like a good
All right, it's going up. It's going up. The ante is now increased. It's now 2 pieces of candy.
It's like
Sit.
a good K-toss.
Okay, it's no. The next good answer is gonna get 2. It's the ante has been raised. It's like the jackpot is now increased. All right, so let's go. All right. I wish I had known this was so
42. 21. The answer to the world is 42.
I wish I knew this last year. It would have made life so much easier. This is like great. Okay. All right. Quiet. Okay. Shh. Listen up. Okay. What's the first thing I need to do in these pretzel problems? We're gonna make our free body diagram boundaries. Okay. Guys, these aren't just given to any right answer. They're given to like really good right answers. Okay. So what are my objects I'm gonna make the free body diagram boundaries around?
You have the rock. You also have
the rock.
And then you also have the weight.
Wait, the weight. And then the what? Okay. Now the guys. Okay, the weight is actually the reason I'm going to put the weight in there is actually necessary. I'll tell you why. Because for the same reason as the guys' hands were necessary earlier, what's not necessary are these 2 guys. Because at the end of the day, when I pull either side, my forces are the same, right? The problem is here I have an unknown, which is the tension. And if I put the weight in here, I'm not necessarily sure what the tension is. Okay? Okay, so let's put the forces. What forces do I have on this rock?
Tension.
Going which direction?
Right and left. And then also you have F1 and F2.
Okay, up and down.
Okay, we're going to put the tension. The one tension we care about is the big rope. We're going to put it up. So now I'm going to have the force. Okay, I'm going to have down for F of G. What else am I going to have? I'm going to have F1, right? And F2. What else do I have? Normal force going up. Okay? Everyone clear on that? Yeah? Okay. So, shh. Okay, so I'm going to move this over to the side. There we are. Okay. Guys, we have 5 more minutes. Stop packing up. Okay. Can you put the bag down so I can see you, please? Guys, 5 minutes out of 45 is a huge amount. It's huge. Okay? It's 5 divided by 45. It's like 10%. It's over 11%. I want an exact number. It's over 11%. Okay. I am a calculator. All right, what?
I am now
All right, what forces are coming off this block here? What forces are coming off this block, guys? Shh. Which direction?
Negative.
How many tensions do I have? 2. What else do I have?
There's FBY.
Okay, there's some sort of FBY, and we ignore all that inside, right? Let me do this way. All right. There's my other one. Okay. Because I'm on different layers. I love it. Layers. Okay. And then what forces do I have here, guys? What forces do I have here? Tension going which direction? Up. Tension up. And then what do I have down? FG. Okay. So now I turn the layer off. Okay, there's my layer off, right? So now I can take... Around the who? The bags? Oh, the guys? Oh, because at the end of the day, the guy pulling on the rope, F2, is going to be the same as the tension of the rope and the same as the pull. You can do that. There's nothing wrong with doing that. I'm just skipping one step. Does that make sense? Because at the end of the day, I'm going to have a tension coming off one side and the tension coming off here, but the tension is going to equal to F2, right? Okay, so I bring that over here, and I bring that over here, okay? So now I can write my equations.
Right.
All right. What are my equations for number 1 here?
Number one.
How many directions of force do I have? 2. Some of the forces in the, you pick?
Why?
Sure, Y. What are my forces I'm summing up?
Equals positive 10.
No, give me the always variables first.
And then
Plus
plus
FG.
T.
T plus, always positive in this case. FG.
FG plus FN.
Okay, let the positive and negative come out of the value. Okay, all right, and that's just it's just the way I'm suggesting to do it to make it easy. Don't make a mistake. That's going to equal what?
0.
First, net force. Now, what is it in the vertical direction? Is it 0 or not? Do we know that? We don't necessarily know. We'd have to do some calculations. But let's make an assumption. Here's the double candy question. Here's the double candy question.
42! No!
If my rock is moving up versus standing still, in this scenario, how would I know from the math? What would tell me that my rock is moving up? What would be negative? What would be negative?
Here, it says force gravity moves up.
What would be negative? What force?